between the two of them. And the uncertainty comparison, it's better filled in the case of ISO 3, but the tail has very low values. But you can see that the uncertainties look like, at least the lower ones look like they're not too far off what they're supposed to be. The higher ones are probably a bit too high. And for 12, the first two bins look like they're a little bit too low, and the rest looks like they're too high, actually. On the AMT in 2019, we have this quite strong hump on the SST difference, and this is for all the data. There was actually a problem with ISO 7 on the last third of the cruise, and you can see that in the histogram of the uncertainty here. And I'll show the data in the next slide. If that's excluded, I look a lot closer, and that's ISO 3 in histogram of the uncertainties here. And again, it looks like the low ones, uncertainties in ISO 3 are probably slightly too low, and the higher ones are too large. You can see it even worse on ISO 7, but that's mainly due to issues with the instrument in the last third of the cruise. If we exclude that data, you can see they agree within 13 millikelvin. Still something funny going on ISO 3, but it's not as bad as it was. And the uncertainty plots show again lower ones are probably slightly too low, and the higher ones are too high. And finally, the lake surface temperature validation. We only have per pixel uncertainties on ISO. The KT15 from KRT only had a fixed uncertainty, so you don't see anything in the histogram. And the temperature difference here is slightly higher than the ISO to ISO and ISO to sister comparison with 60 millikelvin. And on ISO, it looks again that the lower uncertainties are slightly too low, and the higher ones are not far off too high. So with some of the uncertainties being too large, we came up with a new model for dealing with that, because from our understanding, the large uncertainties come from the roll dependence of the emissivity. So we filtered the roll measurements on the instrument with a Hanning filter, which has a length of 11. And we also did sky and sea signal over a longer time period, center weighted average, to get some history of the data into the uncertainty. And that variance was added to the signal both for sea and sky for the internal calibration. And finally, because we're still probably missing some of the uncertainties, we decided to add SST weighted standard deviation as a geophysical indicator to have some indication that something is going on. It's not that the instrument is more uncertain, but the actual geophysical SST, if you compare it to another instrument, could be more uncertain. And the plots at the bottom are from the MT of 2018 data. So version 1 was what we've seen so far. This is some nice thermal variability here on the cruise. See the SST plotted with the uncertainties on top of it. And it's not very sensitive to it, but from the comparison we've seen, it does an all right job. Version 2 reduces the overall uncertainty, but adds bits where there is more variability in the sky and sea view. Version 3 adds uncertainty which is basically geophysical component added to this one, where there's uncertainty in the SST. And if we validate that new model against the same 4 cruises as we had before, with the same plots as we had before, so the green line is the theoretical limit again, the blue is the standard deviation of the binned temperature difference, the magenta line is the mean of the binned temperature difference, and the red is the median plus standard error, and again the histograms at the bottom of the binned data values. We've seen these two before, so this is the new version 2 on the top right hand corner now. You see it seems to perform well further into the uncertainty values, but this one here which is too low for that temperature difference. It should be further along, so it's not perfect. And if you add that geophysical inversion, uncertainty in version 3, this line actually moves further along, but it's still not quite far out enough on the plot, because it's still, this actually goes to plus minus 2 Kelvin, so it's still not quite far enough along. And again, while there are more uncertainty values now, higher ones that don't seem to represent the data perfectly, or still not represent the data perfectly. If we look at the MG 2018 data, which did a fairly good job to start with, here actually the new uncertainty ISO models reduce the uncertainties, but do a very good job in version 2 and do a reasonable job in version 3. It's just, it adds some high uncertainty bins here, but they're probably a bit too high. The MT data from 2019. Again, the new version 2 and version 3 start representing the lower uncertainties better, but it still has a problem with overestimating some of the higher uncertainties. And this line is again not quite big enough, so it needs to be further to the right. And finally, for the lake surface temperature, we move from version 1 to 2, so get probably a slightly better spread, but not ideal. And version 3 does do the lower ones really well, but the higher ones are probably slightly too high still. So in conclusion, the field intercomparisons are essential for uncertainty validation, but the data is sparse, especially for higher uncertainties. From those 4 cruises, over 70% of the data is below 0.25 Kelvin, and over 95% is below 0.05 Kelvin. However, the histograms show that the temperature difference between the 2 instruments is larger at times than that. So one of the conclusions from these experiments is that the original total ISO uncertainties were too large, but the instrument uncertainties look about correct. That came out of the ISO sister comparison, and they look very similar. And the main reason for the total uncertainties being large is the role dependency of the emissivity uncertainty. And the newer version 2 and 3 address that role dependence and reduce it by filtering it. But it's clear that we're missing something in those uncertainties, especially the higher ones. That's partly due that there might be some real physical differences not measured, and some of this is probably more a matchup uncertainty than part of the instrument uncertainty. And we know that a lot of the type B uncertainties are non-perfect, and one of the big issues here is emissivity. Some other ones in the instrument, but they're probably less relevant to this. And there might be still some issues with cloud variability.